Hello students, I am Dr. Mrs. Sangeeta Wankhede, Head of the Department of Physics from KDK College of Engineering. Today I am going to deliver lecture on lasers. So content of the laser this in our syllabus is first is introduction and quantum transitions, absorption, spontaneous emission and stimulated emission, metastable state, population inversion, pumping schemes, and laser properties. In spatial and temporal coherence of the light wave, so there principle and working of helium neon laser, in ruby laser, and applications of lasers. First, we'll understand these what are the learning objectives of this chapter laser. We have to understand the basic laser physics, describe the concept of stimulated emission and what is an active medium, then learn about the types of laser and their applications. These are the objectives. So what is laser? It's it is the acronym for light amplification by stimulated emission of radiation. Okay. Now what is the difference between ordinary and laser light? So ordinary light is incoherent, okay? It is highly divergent, it has low intensity and it is polychromatic. But laser light is coherent, less divergent and it is of high intensity and it is monochromatic. That is means single wavelength. So these are the characteristics of laser. Monochromaticity, coherent, high intensity, it is unidirectional and it's less divergence. Okay. Then what is coherence length and coherence time? So there are many light waves are traveling. So the length of the wave train over which it is perfectly remaining sinusoidal, that is known as coherence length, and it is given by C into T coherence, that is C into delta T. Delta T, that is coherence time. The coherence time, the time over which the wave train is perfectly sinusoidal, that is known as coherence time, and it is given by coherence time is equal to delta T, that is equal to 1 upon delta mu. So L coherence is equal to C into T coherence. So C into delta T, C, that is equal to C upon delta mu. Okay. So because delta T is equal to 1 upon delta mu. Okay. And as we know, mu is equal to, frequency is equal to C by lambda. So delta mu is equal to, if you take its differentiation, then it will become minus C delta lambda upon lambda square. So finally after calculation, it will give an L coherence is equal to lambda square upon delta lambda. So all these formula, L coherence is equal to C into delta T, then L coherence is equal to C upon delta mu, and L coherence is equal to delta lambda square upon delta lambda. These all formulas are important. Okay. Then what are the three quantum processes in laser? Okay. That is stimulated absorption, spontaneous emission and stimulated emission. Okay. So what is stimulated absorption? That we are going to study. So normally we are considering the atom uh, consists of two energy levels. Means two energy levels in atom will, for our convenience, we will consider. Actually any solid consists of many number of atoms, and these atoms are characterized by the energy levels. Okay. So for our discussion we will consider two energy levels, E1 lower, that is ground state, and E2 is the upper energy state, that is the excited state. So when the photon of energy h mu is incident in the medium, atoms, ground state atoms, normally ground atoms have tendency to remain in the ground state. So when the photon interacts with the medium, atoms in the ground state absorb the energy and they are excited to the higher energy level. So, and the number of absorption transitions are given by B12, that is the Einstein coefficient. Okay, this quantum transition processes, they are that is the main principle of this these quantum transitions are the main principle of working of laser. Okay. It is given by Einstein. So here in this process, stimulated absorption, Lower atoms will indicate by A, and H mu, A plus H mu is equal to A star. A star is the atom in the excited state. Then here this is a process. Okay. So here photon is interacting with this atom, and then atom will go in the upper energy level. Okay. So this is the stimulated absorption. Then what is spontaneous emission? So when the atom will go in the upper energy level, that is excited state E2, it will not remain there for longer time, because its lifetime of this atom is very less, that is of the order of 10 raised to the power minus 8 seconds. It is unstable state. Okay. So atom will automatically come down uh, um, before 10 raised to power minus 8 or after 10 raised to power minus 8 seconds. Okay. So it will come down spontaneously. So this is given by A star is equal to A plus H mu. Okay. And so this, how will you define it? The process of emission of photons by an excited atom on its own without the influence of external agent is called spontaneous emission. And this reaction is given by A star is equal to A plus H mu, and number of spontaneous transitions are given by A21 N2 into delta T. Then third process is stimulated emission. So a spontaneous emission, this we are showing. So this atom is coming down now on its own, and while coming down it will emit the that whatever photon was absorbed, it will emit the photon. Okay. So this is the spontaneous emission when atom will come down to the ground state, okay, from excited state, and while coming down it will emit the photon. Okay. So this will be spontaneous. This is again it is shown here. Now stimulated emission. In the case of stimulated emission, if you don't want to wait for spontaneous emission, and if we, whenever it is we want to bring down the atom, then external photon is interacted with the atoms in the excited state. Okay? And when the external photon interact with the atom in the excited state, it will come down to the ground state, and while coming down, this interacting photon will not be absorbed by this excited photon, but that interacted photon and the emitted photon, okay, both will travel in the same direction. So because it is a excited atom is already there, so it will not absorb the photon. So this process is known as the process of force photon emission by an excited atom. Okay, by an excited atom is known as stimulated emission, and this reaction is given by A star plus H mu is equal to A plus 2 H mu. So N is, and number of stimulated emission transitions are given by B21 N2 into delta T into Q. Q, that is the photon density. Okay. That is rho mu is there, but we can use photon density also. So it is shown here like this. Initially it is uh, stimulated emission. In this stimulated emission, the atoms will come down, and while coming down they will emit the photon. So they will remain in metastable. This about metastable state I will explain you what is metastable state. So in metastable state, so that definition we will discuss later. Now what is the difference between spontaneous emission and stimulated emission? So spontaneous emission is a random process. This is not a random process. It is spontaneous emission is not controlled from outside. It is stimulated. It is controllable from outside. Here resultant light is monochromatic, incoherent. Okay, but here resultant light is in stimulated emission. It is highly monochromatic and it is highly coherent. Here net intensity of the emitted light is how many number of atoms are emitting the photon. So that is I total intensity is equal to n into I. I is the intensity of light emitted by one atom. Okay, that is photon, and the net intensity is given by I total is equal to n square I naught. Okay, so now condition of light amplification. What is the condition of light amplification? So for light amplification, that means in which case the laser is emitted. So stimulated for emission of laser, number of stimulated transitions, emission transitions should be increased. So we'll take the ratio of stimulated emission transitions divided by spontaneous emission transition. So by using previous equations, here we will get the density, photon density, that is B21 upon A21 is constant. So this ratio will be equal to photon density. Second condition is the when we will take the ratio of stimulated emission to absorption transitions, then after taking ratio we will get this B21 upon A12 is both are constant, then we will get N2 by N1. So from these two conditions it is seen that the stimulated emission transitions will be increased if photon density is large and if N2 is greater than N1. Okay? So that is also known as when N2 is greater than N1. N2 means the number of atoms in the excited state and N1 is number of atoms in the ground state. When this condition is achieved, it is known as state of population inversion. So this is explained here. In normal condition, that is thermal equilibrium condition, normally atoms have tendency to remain in the ground state. Okay, so that is thermal equilibrium condition. So and it is given by Boltzmann equation, N2 by N1 is equal to e raised to the power minus delta E upon kT. K is the Boltzmann constant. So but for a laser, okay, emission, so population inversion should be achieved. So population inversion is a condition in which population of upper energy level, that is N2, is greater than the population of lower energy level. So this when for light amplification this condition should be achieved. This is known as population inversion. Then what is metastable state? Okay, as we have seen that in excited state atoms do not stay there for longer time, but just now we have seen light amplification, that is N2 should be greater than N1. So the atoms will not stay in excited state. So one more state will be available there, that is metastable state, that will be it will be in between excited state and the ground state. So atoms stay in metastable state for longer time, that is of the order of 10 is for -6 to -3 seconds. Okay. So it is a metastable state, is a state where atoms remain for longer time, okay, than the normal state. Okay. So for light amplification, metastable state is required, okay, to achieve population inversion. Now, what are the components of laser? There are three main components of laser: active medium, pumping agent, and optical cavity resonator. So these are the components. Okay. So what is active medium? It is the medium in which light gets amplified, which hosts the active centers. Okay. So and active centers are those atoms which are responsible for stimulated emission. Now, what do you mean by second component, pumping? So, the process of supplying energy to the medium with a view to transfer it into the state of population inversion. This is known as pumping. There are three techniques to achieve population inversion: optical pumping, electric discharge, and direct conversion method. Okay. Now, what do you mean by Fabry-Perot or optical resonator? Or resonant cavity. So it consists of two opposing plane mirrors. That is, one front mirror is semi-transparent mirror and it is 90% reflector. Back mirror is fully polished, fully silvered, and it is 100% reflector. And in between these two mirrors, there is active medium. Okay. So this is obtained. It is required to achieve this laser emission. Okay. So these are the 6 steps. 5 steps are there, in which first initially atoms will remain in the ground state. Then through pumping, population inversion is achieved, then then spontaneous emission will start. Then these stimulated emission, that spontaneously emitted photon will trigger the stimulated emission, and stimulated emission will be augmented in direction of optic axis only. Okay. And then light amplification will here start, light oscillations will begin, and means through optical feedback. Okay, the number of photon density will increase, and finally these oscillations build up and laser beam will come out from the front mirror. Okay, so then condition of steady state oscillation of in optical cavity resonator is that the length twice L is the length of optical cavity resonator, should be equal to m into lambda. So this is the condition. Then what are the pumping schemes? Okay, there are three pumping schemes: 2 level, 3 level, and 4 level pumping scheme. But 2 level pumping scheme will not lead to laser action. Only 3 level and 4 level schemes lead to laser action. So in 2 level pumping scheme, there are two levels we are considering it. In this case, the atoms, the photon will interact with this. We will discuss 3 level pumping scheme only because it will lead to laser production. So in this case, three energy levels are there, that is E1, E2 and E3. E2 is metastable state. Okay. So here initially through pumping, ground state atoms are pumped to the E3 level. E3 is excited state, it is unstable, so atoms will not stay there for longer time. They will through non-radiative transition, they will spontaneously come to E2 level. E2 level is metastable state. Okay. Here atoms will stay there for longer time and population inversion will be achieved. Then one of the spontaneously emitted photon will trigger the stimulated emission. Okay, and laser transition will start, means laser beam will be produced. Okay. But here major disadvantage of 3 level pumping scheme is its efficiency is less, and here high pumping power is required to achieve population inversion, because population inversion is to be achieved with respect to the ground state. Okay. And there are many number of uh, atoms in the ground state, and more than half of the ground state atoms are to be pumped to the upper energy level. Okay. Then we will see the 4 level pumping scheme. Here there are 4 energy levels. Initially atoms are in the ground state E1, then through pumping they are pumped to the E4 level. E4 is that is excited state. Okay. Through non-radiative transition they will come to the atoms will come to the E3 level. Then E2 level is virtually vacant. So through using only less pumping power also population inversion will be achieved. Then one of the spontaneously emitted photon will trigger the stimulated emission and laser beam will be emitted. So here very less pumping power is required, okay, to achieve population inversion, and here the these laser beam will come in the form of continuous wave mode. Okay, so that is the major advantage and it is more efficient. Okay. Then we will see the types of laser. There are three main types of laser: solid state laser. In case of solid state laser, ruby laser, neodymium YAG, neodymium glass lasers are there. But in our syllabus, we will discuss on ruby laser. Then gas laser, there are helium neon, helium cadmium, carbon dioxide. Then nitrogen lasers are there. In our syllabus, we will discuss helium neon laser. Semiconductor lasers are also there. That is, these are the electronic devices. Here, gallium arsenide phosphor. So mainly we will discuss in this lecture ruby laser and helium neon laser. So ruby laser is the first solid state laser developed by Maiman in 1960. Okay. It consists of ruby rod, cylindrical rod is there. That is, that ruby crystal is made up of aluminum oxide Al2O3 doped with 0.005% chromium ions. Okay. So it is surrounded by this helical flash lamp. Okay. Initially, the atoms are in the ground state. Okay. So here, this is the construction of ruby laser. Okay. It is ruby rod is of 4 centimeter in length, diameter is 1 centimeter. Okay. Front mirror is partially silvered, and here back mirror is fully silver. So it is made up here, optical cavity resonator is made. When the power supply is switched on, high voltage power supply is switched on, the this flash of white light will incident on this ruby rod. Okay, here though the Al2O3, aluminum, oxygen and chromium ions are there, but here chromium ions are only active centers. Okay, so aluminum and oxygen are inert, they do not take part in lasing transition. Okay, so here we'll discuss its working using this energy level diagram. Okay, so chromium, this is the energy level diagram of chromium atoms. Okay, so initially atoms are in the ground state E1. So it is uses 3-level pumping scheme. Here E3, it has a chromium atom can absorb green and blue component out of white light, which will incident on the ruby crystal. It has two absorption bands for green and blue component. Okay, so this is blue, its wavelength is less. Okay, and green component its wavelength is more. Okay, so that is here for this is green, wavelength is less, so energy will wavelength is more, it is around 5500, and here it is around 4000. So for blue component energy band is at upper level, and E3 for green component it is energy band is at lower level. So here after absorption these atoms will stay there for very less time because both are excited states are unstable. Then through non-reductive transition the atoms will come in the metastable state. Then after achieving population inversion, one of the spontaneously emitted photon will trigger the stimulated emission and laser will be produced. Okay, so its wavelength is of the order of 6943 angstrom. Okay, then we will see the next laser. So here also here disadvantage is that here it will laser beam will be produced in the pulses. Okay, then helium neon laser, it's this optical cavity resonator, it's uh, discharge tube is there. Here very narrow tube is there, and its length is 50 centimeter, diameter is again 1 centimeter. Okay, and it was developed by Ali Jawan in and his co-workers in 1961. So this glass tube is sealed by glass windows. These windows are inclined at Brevister's angle to get the plane polarized light. Here front mirror is again semi-transparent and partially silvered, back mirror is fully silver. Okay, that is, so it is optical cavity resonator, its length is twice L is equal to n lambda. Okay. Its structure is, and electrodes are there, electric air pumping method is electric discharge method. Okay. So here partially front mirror is partially silvered, here is side, this side, and back mirror is 100% reflector. Okay. So electrodes, electric discharges pass through this. So 50 centimeter long and 1 centimeter diameter, and helium neon percentage is their ratio is 10 raised to 1. So here helium neon atoms are active centers. Okay, and helium atoms is efficient to excite the neon. Role of helium atom is to excite the neon atoms. Okay, so and here I will explain in the energy level diagram. Here helium at the energy level diagram of helium is there is this, and neon energy level diagram of neon is this. So here you are seeing F1 is ground state, F2 and F3 are upper energy level, but they are metastable state. Okay, neon there are 6 energy levels. E1 is ground state. Okay, E6 and E4 they are here metastable states. Okay, their energy level is 20.66 E6. Okay? Here it is 20.61. So when the electric discharge is passed, the electrons electric current passes through the optical cavity resonator medium. Then helium atoms, they will collide with the helium atoms. Electrons will collide with the helium atoms. Helium percentage of helium atom is more and they are lighter. That's why electrons will excite the helium atoms. Okay? And helium atoms will go in the F3 and F2, both are metastable state. Then through resonant energy transfer, okay, they will transfer their energy to the neon atoms. Okay, and these E5 and E6 are virtually vacant state. So there is a population inversion will be achieved between E6 and E5, E6 and E3, E4 and E3. So therefore there is a lasing transition in this. Here one of the spontaneously emitted photon will trigger the stimulated emission. So here in this, in between E6 and E5, population inversion will be achieved and laser beam of 3000 33,900 angstrom will come out. Okay. In the lasing transition between E6 and E3, laser beam of 6,328 angstrom will come out, will be emitted. Okay. And here 11,000 between E4 and E3, 11,500 angstrom laser beam will come out. Then after lasing transition, these atoms will come to the E2 level. Then E2 level is again metastable state. So for continuously means atoms should be available continuously in the ground state. So these atoms are to be brought to the E1 level quickly. For that they will that discharge tube is narrow and these atoms in the E2 level will collide with the wall of the discharge tube and through collision they will come down to the E1 level. Okay, and they will give up their energy and come down to the E1 and they will continuously available for pumping. Hence we are getting helium neon laser in CW mode. So whatever I explained, it is shown here. Okay. Now lastly we'll discuss the applications of laser. Okay. There are many applications in industry, in medical science, in astronomical and geophysical applications, then metrology also, then applications in communication. There are many applications in defense and environment monitoring and uh, scientific research for that. So these are the applications are shown here. Okay. Defense application. Okay. So optical communication system, for that also where laser and science and technology. In holography, then for security hologram also. In medical applications, mainly in surgery, laser beam is used. So finally this summary, I will summarize what we discussed today. So what is laser? Laser is a source of light that emits intensive and highly directional beam of light. In this process of stimulated emission, photons are multiplied, hence the amplification of light takes place. Ruby laser is a pulse laser having low efficiency and helium neon laser is a continuous wave mode laser having high efficiency, and laser has broad applications in various fields of modern technology. Thank you.